Hello everybody. So this is the first lecture of the early universe, continuation of the very good job which has been done by Francesca, talking about the cosmology. So first of all, just to repeat that the logistic of the course is the following. So we have a schedule, we have coordinates and contact numbers of coordinators, we have an office hours, and we have the plan. So the plan is to first of all to give lectures during the rest few weeks till the 1st of December, and to present the following problem sheets. So the problem sheet number 4 and 5 are left. Just to remind you that assessment consists of two parts, and both parts are very important: 90% of exam and 10% of the problem sheets. So marking will be done for all solutions and will be for all problem sheets, providing all solutions, and will be posted on the Blackboard. The problem sheets are very important, so they have similar examples of the questions which will appear at the exam. So in the first lecture I will talk about the density of the universe and dark matter, and followed by microwave background, Big Bang nuclear synthesis, and inflation. Finally, I will end up with the lambda CDM models. To remind you that I also use Me2 as a great tool for quizzes and communication responses. So this is the unique number 179205144. This number will be the same for the all early universe course. The aim of the first lecture, first 2 hours, is to discuss the energy budget of the universe and provide evidence for dark matter and its experimental sources and learning outcomes related to this topic. So first of all, this is the result of quiz, and as majority of you correctly answered, indeed the density, the matter density and the energy density of the universe is about 5 protons per meter cube. So this is the brief this summary of the first lecture. Therefore, I will not go through all details, similar to what Francesca did, and just a summary that we have the matter energy budget of the lambda CDM model at T0 as follows. So we have 68% contributing from so-called dark energy. We have 32% contributing from matter, and very negligible amount contributing from the radiation, about 10 to the minus 4. But the most interesting thing about the matter is that the matter, though it contributes 32, the most of the matter which contributes to the energy budget of the universe we don't know about. We have no idea about this matter and nature of this matter. Well, the point is that there is a robust predictions and a clear indication, a robust prediction of Big Bang nuclear synthesis, and clear evidence about something which we call dark matter, which contributes 5/6 of the total matter budget of the universe. On the right hand side there is a famous plot, which so-called the concordance plot of several independent experiments, including supernova data, which tells about certain relation between dark energy, matter density, and its linear relation, which based on the supernova measurements. On the other hand, there is a so-called orthogonal or completely independent measurement of the energy matter budget of the universe coming from fitting of CMB data. CMB is cosmic microwave background, which tells us that universe is flat with a very good precision, and eventually which crosses of the region which defined by a supernova in quite definite point with respect of mass density and vacuum energy density. So the mass density is about 0.3, and it's also coincide with the measurement which done by clusters. It's really quite amazing picture of concordance of cosmological data. In other way, one can summarize this information and another way using the pie chart, and well, this pie chart again indicates the amount of dark energy in dark matter, and only 5% amount of matter energy budget of the universe coming from ordinary matter. So this is the equation which well, indicating that the main contribution to the matter energy budget of the universe comes from, at present, comes from cosmological constant, dark matter, and baryonic matter. Baryonic matter is the matter which is protons and neutrons. Essentially, it's atoms, which, well, distributed in our universe, mainly in the, well, stars and intergalactic media. So again, the matter of density of ordinary matter is referred as baryon density omega b0 at present. So first of all, talking about the matter, one can look at what's the amount of matter in stars, looking at luminosity of the star and relation of luminosity in the mass. And looking at this, one finds that the ratio of energy density or matter density coming from stars to the critical density is 4 × 10⁻⁻3, which is definitely not explain. It does not explain the amount of matter in the universe, observed and confirmed from different independent measurements, from other independent measurements. Now we can take a look at matter at hot low density gas, which actually contributes about 10 times more, amazingly, than stars. So, well, it's just compared to 4 × 10⁻⁻3. It's 3% to the total 3% to the total density, but 3% is still much lower than 30% of the total matter density of the universe at present. And looking further, one can actually, well, estimate the density of the baryons coming from estimation coming from a Big Bang nuclear synthesis, and this is estimation gives you 5% of the baryonic matter, and this estimation comes actually from the most precise estimation of baryonic density comes from CMB data, which we discussed later on along this course. These two pictures of the cosmic concordance present the evolution of the precision of the cosmological measurements during the decades, indicating that the latest Planck measurement really pinned down the Planck measurements along this line pinned down the properties of the so-called standard model of cosmology down to about few percent level. The difference between the total matter density and baryonic matter density is significant, is about 27% of the total budget of the universe, and this difference is referred to something which we don't know. It's called dark matter. Actually, the evidence for dark matter comes from several independent measurements and experiments. So the very early one, the first one, came from galactic rotation curves, which can be estimated using simple Newtonian dynamics, because the main mass of the stars in the galaxy is concentrated in the certain compact region, and therefore it allows us to apply Newtonian dynamics, very simple laws. So one can find that the velocity of the star will be dropping as 1 over square root of radius if the mass is fixed. And indeed, actually for galaxy, the mass is fixed well in a certain region, which is Rs, and the typical value of Rs for our galaxy, for example, is 4 kiloparsec. Therefore, one can estimate the velocity distribution of the stars in our galaxy, and the estimation tells that what we expect is that velocity, the rotation speed or velocity, will be falling according to 1 over square root of r, as mentioned above. What is observed is completely different. It's actually what is observed, that rotation speed amazingly constant, as you can see, which is actually was clear indication that something going on. There is some matter present, usually as a kind of halo. It could be most of the model predicts spherical halo around the center of our galaxy containing dark matter. So the next indication of dark matter relic density is the rotation, actually dynamics of the galaxy clusters. These slides are just indicated again details on the dark matter and rotation curves in the galaxy, which I will skip because these details I explained at lecture. So here is a brief summary. It's actually not quite brief, but I'm trying to be brief this time. So talking about the dark matter in clusters, one can use a virial theorem which apply to much more complicated system than in case of galactic rotation curves. And as a summary, one actually estimate again the amount of dark matter at the scale of galaxy clusters. One can see, and actually one can estimate an estimation shows that the omega dark matter at the cluster scale is 0.2. It's still slightly below at 0.3 or 0.20 0.3, and this again tells us that something which we don't account for. What we don't account is the actually dark matter distribution between the clusters. So more precise estimation would definitely tell us that dark matter density will be around 0.27, in concordance with other independent measurement of dark matter. So, as a summary of independent confirmation of dark matter, I'd like to stress that the first one was galactic rotation curves. Then, of course, the cosmic microwave background and feats of cosmological parameters, feats of WMAP and Planck results. There's also dark matter existence is confirmed by simulation of the large-scale structures, gravitational lensing, dynamics of the galactic clusters, and especially bullet cluster. The bullet cluster requires a special actually stress, which I will actually give afterwards. I'll state different solutions for dark matter puzzles. So one of the solution is possible solution which actually fails, but attempt it's always good to assume something. Is massive compact halo object or matches. For a long time it was believed that dark matter can be explained by matches. However, the gravitational microlensing data indicates that such objects like giant planets or brown dwarfs definitely not enough to contribute to that amount of matter, in this case of dark matter. And on the other hand, the gravitational lensing is a great confirmation of dark matter, and gravitational lensing it can be used to predict amount of dark matter at long distances. This is the gravitational microlensing, which it has much weaker and blurrier effects comparing to gravitational lensing. Magnification of Newtonian dynamics, or MOND, was very strong proposal and explanation so far, till actually bullet clusters has been discovered. Yes, you can explain modification of the galactic rotation curves by adding some by modifying the Newtonian law at some scale. Modification of Newtonian law at certain scale will lead to appearance of additional acceleration at the distance, at the large distances, which would lead to explanation, can give an explanation of the galactic rotation curves. However, if you look at bullet cluster, this is the two galaxies. There is the system of two clusters of galaxies which actually collide, and there are several such objects have been observed, and each of them actually indicates that there is something which pass through each other, the big mass which is passed through each other, and this big mass is observed via gravitational lensing effect, and this mass is not participate in the kind of collision. On the other hand, there is certain mass which is normal matter interacting with known forces, make some heat, and actually this matter also the part of the picture. So the bullet cluster presents the picture which can only be explained by two different fluids, very distinct by their nature. One of them is dark matter and another is ordinary baryonic matter. Primordial black holes as dark matter candidate also fail to be true because of again microlensing effect. The microlensing observation did not confirm the hypothesis of the primordial black holes explaining dark matter. Now the question is, can standard model particle be dark matter candidate? And your quiz, you indicated yes, potentially they could be neutrino, as more than 95% of you suggested. Well, however, neutrino, in case of neutrino, there could be a problem, and the problem is related to the fact that dark matter in the form of neutrino will be relativistic, and therefore neutrino would not explain the formation of the large-scale structures, because just mechanically it would not allow the forming large-scale structures, since the speed of neutrino is around about speed of light. In other words, well, if you require the presence of the cold dark matter, because relativistic particle like neutrino will be hot, which is excluded by a large-scale structure of simulations. So if you require dark matter to be neutral, stable, colorless, non-baryonic, and massive, cold or warm, then there is no such dark matter candidate in standard model. That's a quite solid conclusion. So dark matter implies new physics beyond the standard model, and this is a very appealing statement and consequence of the experimental data. The data and explanation for dark matter, with contributing 27% to energy matter budget of the universe, requires about 1 particle of dark matter per 1 cubic meter if the mass of the particle is 1 GeV. If not, then the mass of the particle just scales as it's shown in this formula. What are theories can explain or suggest dark matter? Actually, there are quite a few theories where dark matter is the new heavy weakly interacting particles, and such theory exists for a long time ago already. They must predict stable or quasi-stable at the cosmological scale dark matter, again neutral weakly interacting heavy particle, and among the theories there is a supersymmetry, some extension of QCD with the axions, which are actually extremely light, but they are not thermalized. They actually, there is a different mechanism which still permits large-scale structure formation. There is also super partner of axion, Axina, which can be quite heavy. and actually quite a few other theories, like x-dimensional theories and theories with the heavy right-handed neutrino, etc. This picture presents the extremely large scale of the mass and along the x-axis, and strength of the interaction along the y-axis, and the central part in this picture plays WIMPs. They occupy the central part of the picture. WIMPs means weakly interacting massive particles. This is a summary of these particles is beyond this course, but in any case, for reference, I mention this plot as well as the reference where I took it, and different possibilities for different options for dark matter candidates, just for the further reading and references. How to detect dark matter? If dark matter weakly interacts with standard model particles, you can detect dark matter using so-called direct searches, when dark matter scatters off the nuclei, and nuclei are the part of the forms the body of dark matter search detectors. Dark matter can annihilate with each other if dark matter is symmetric one. In case of asymmetric dark matter, when you have only dark matter particle but not antiparticle, dark matter cannot annihilate. But if dark matter can annihilate, so if there is some particle and antiparticle present simultaneously in the universe, then dark matter can annihilate and contribute to so-called indirect searches, because if dark matter annihilate, it annihilate to standard model particles, which would be quite energetic like gamma rays, neutrinos, positrons, antiprotons, etc. So any stable particles from standard model coming from dark matter annihilation would contribute to indirect searches of dark matter. And of course, one can search for dark matter at colliders once you can produce it. Direct dark matter search experiments are being intensively developed nowadays, and the vertical axis indicates the sensitivity of these experiments to dark matter interactions and strengths of dark matter interactions with standard model. So essentially, y-axis is directly related to the strength of the interaction of dark matter with the standard model particles. And the most exciting data now, and the most sensitive data at the moment, comes from Xenon 1 Ton, which already started its operation, and it produced the first data. And direct detection, well, as I mentioned, it could be gamma rays or positrons and antiprotons. I'm not going to talk about this in details. And the next topic and the next piece of information about the hunting of dark matter at colliders, as I mentioned in my lecture, dark matter, the requirement of stability of dark matter, if dark matter is stable, requires dark matter be in pairs in the Feynman diagram. So you produce dark matter in pairs always if dark matter is stable, and therefore such process is a typical one which takes place at the LHC, and this circle indicates the cross section of the detector. If you just produce dark matter at the collider, a dark matter pair, then you observe nothing, because dark matter is like in neutrinos. For the detector, at least at Large Hadron Collider, they are invisible to the detector at a Large Hadron Collider. However, if initial state particle, for example, radiates some energetic standard model particle, or any energetic standard model particle, in this case it's gluon, then there will be a very striking signature, because gluon, or any jet coming from any standard model particle, will be recalling invisible dark matter. So you will have kind of large missing transverse momenta, though initially you would expect the transverse momenta is balanced, because initial transverse momenta is zero when you collide protons, and then suddenly you see one particle goes in one direction and it recalls nothing. It's quite a striking signature of dark matter. Just to conclude, that there is a symmetry or great complementarity between different dark matter search experiments. So to start with, again to repeat, if dark matter interacts with standard model, it can effectively annihilate the standard model particles, because weak interactions are not that actually weak. It's the name, but the strength of the weak interactions is twice as large as electromagnetic ones. But weak interactions has a feature: dark matter does not interact with the photon. That's why it's dark. So dark matter can annihilate through the weak interactions to standard model particles, and at the same time dark matter can scatter on the nuclei and then can be efficiently detected or potentially detected by direct dark matter search experiments. And if we go along the red arrow, then you can see that this diagram indicates that you can effectively search dark matter at the colliders. And the final remark is that dark matter search experiments, different dark matter search experiments, they're very complementary to each other, which gives us a great hope to actually discover dark matter in the near future. This is the end of the summary of the first 2-hour lectures, and the next time I will discuss the cosmic microwave background. Thank you.